Hi, this is Bruce Jameson from the University of Calgary. This is a short video about two recent studies that looked for trends in snow climate or avalanching in British Columbia. This slide lists the authors of the two papers. I'll describe how to find the articles online at the end of the video. In studies of climate change, one can look ahead with models or look back with data. These two papers look back at data. From Rogers Pass in Glacier National Park, Sacha Belair and colleagues analyzed about 50 years of data. From 6 passes in British Columbia, Alexander Hendrikx and colleagues analyzed about 30 years of data. Our objectives were to look for significant trends from elevations relevant to avalanching and to assess if the significant trends were consistent with climate warming or not. Here's a map of British Columbia. 6 passes in the BC Highways jurisdiction are marked with white circles. Glacier National Park is marked with a yellow circle. Let's start here with the results from the article by Sacha Belair and colleagues. This photo shows a section of the highway east of Rogers Pass in Glacier National Park. Obviously, many avalanche paths can affect the highway. Weather data are available from the Mount Fidelity study plot at 1905 meters, shown here in this old photo. The lower elevation weather data are from the Rogers Pass study plot at 1315 meters, which is an opening in the forest at about the elevation of Rogers Pass. In the following slides, results from the Fidelity study plot are shown in blue, and results from the Rogers Pass study plot are shown in orange. The data were analyzed for early winter, midwinter, and spring. I'll only show the results from December through February, which I'll call midwinter, and from March to May, which I'll call spring. The p-values below the graphs are the probability of getting a comparable trend from random data. In this and many other studies, p-values less than 0.05 are considered significant. In other words, if the probability of getting a comparable trend from random data is less than 1 in 20, we'll call the trend significant. Let's start with the average air temperature over the 3-month periods. In midwinter, we see increasing air temperatures in Fidelity in blue and in Rogers Pass in orange. Both these increasing trends over 50 years are significant because their p-values are less than 0.05. In spring, the trends from the two sites are not significant because the p-values are greater than 0.05. These graphs show the solid precip ratio, that is, the percentage of precipitation that falls as snow. In midwinter, almost all precip falls as snow at Fidelity, and most precip falls as snow at the elevation of Rogers Pass. Neither trend is significant. In spring, less precip falls as snow. There are visual decreasing trends over the last 50 years, but neither of these trends has a p-value less than 0.05, so the trends are not considered significant. Now let's look at trends in the snowfall and snowpack from both sites. This is another old photo of the treeline study plot at 1905 meters on Mount Fidelity. Let's start with the maximum snowpack height, HS, over the 50 years at the two sites. At the Fidelity study plot, during some winters, we see midwinter snowpack heights over 400 centimeters. The trend at Fidelity is too variable, that is, it bounces around too much to be significant, but there is a significant decreasing trend at Rogers Pass. In the spring at Fidelity, the snowpack height almost reaches 500 centimeters some years. Again, the trend at Fidelity is not significant, but the trend at Rogers Pass, 1350 meters, is significant. Now let's look at the trends in the average 24-hour snowfall. In midwinter, the daily average snowfall at Fidelity was often over 10 centimeters 40 to 50 years ago. Now, the midwinter average is usually less. The midwinter trends are significant at both sites because the p-value are less than 0.05. We see less daily snowfall in the spring at both sites. Only the trend at the lower elevation site, Rogers Pass, is significant. This slide shows the maximum 24-hour snowfalls. In midwinter, we see many snowfalls with maximum daily snowfalls over 40 centimeters at Mount Fidelity and also at Rogers Pass. The decreasing trends at both sites are significant. In the spring, the trends are not significant at either site. This graph shows the day of the year when the study plot first became snow-free. At fidelity, this is often between day 180 and day 210 on the left axis, roughly between the end of June and the third week of July. At the Rogers Pass study plot, this occurs around day 150, which is about the end of May. Neither of these trends is significant. Glacier National Park has a remarkable record of manual snow profiles from the tree line study plot on Mount Fidelity. We looked for crusts in the snow profiles from November and December. For winters in which we could not find a melt-freeze crust, the blue bar goes down. For winters in which at least one crust was observed in a snow profile, the bar stands up. Around 1994, the graph shows an increase in early winter melt-freeze crusts. This may be important because a layer of faceted crystals sometimes form on top of early winter crusts, forming a persistent weak layer, which can release natural and human-triggered avalanches, sometimes for a month or more after these layers are buried. The paper by Sacha Belair and colleagues also looks at natural avalanches reported in Glacier National Park. There are a couple of challenges with this part of the study. First, the park makes extensive use of the howitzer, shown here, to trigger avalanches during highway closures. This explosive triggering can reduce subsequent natural avalanches. Also, the daily traffic has increased over the decades, and the reporting of avalanches has also changed. Hence, we were unable to reach conclusions about trends in natural avalanching in Glacier National Park. Now let's look at avalanching at the 6 passes in British Columbia, which are marked with white circles on this map. Alexander Hendrikx and colleagues analyzed the data from these passes, which are managed by the BC Ministry of Transportation. Hendrikx used the Bayesian hierarchical method to analyze about 30 years of records of avalanches reaching or crossing the highway. There were no trends at 4 of the 6 passes. The other 2 passes, Bear Pass and Kootenay Pass, showed a decrease in avalanches. However, the decrease could be due to a change in explosive triggering, so Hendrikx reanalyzed the data using only paths with at least 75% natural avalanches. For the paths with at least 75% or more natural avalanches, Hendrikx found little change for 4 of the 6 passes and decreases at Bear Pass and Kootenay Pass. The graph shows that nowadays there are about 14 fewer natural avalanches per winter reaching the highway than 30 years ago at Bear Pass and at Kootenay Pass. However, this looks a lot like the graph that I skipped, in which all paths were included in the analyses. Also, these 2 passes have had substantial changes in explosive control methods. In spite of our attempt to reduce the effect of explosive triggering on natural avalanches, we are not confident we have done so. A safer conclusion is that there is no evidence of more natural avalanches reaching the highway at these passes. Okay, let's draw conclusions from the 2 studies. First, many of the trends we analyzed were not significant. Each of the significant trends is consistent with climate warming and reduced snowfall. Of the significant trends, more were significant at the lower elevation site, 1,315 meters, than at the tree line site, 1,905 meters. None of the significant trends were inconsistent with climate warming. Last, we found no evidence of increased avalanching reaching highways. Sacha Belair is the first author of the Glacier National Park study. Here he is at the University of Innsbruck. For support and data from Glacier National Park, we are grateful to Grant Statham, Jeff Goodrich, and Parks Canada. Here's a photo of Alexander Hendrikx, who is the first author of the BC Highway Study. For encouragement and data from the BC Ministry of Transportation, we are grateful to Doug Wilson and Mike Boissonneau. I've only shown selected results from the 2 studies. The methods and more results are described in the 2 journal articles, which are freely available online. To find the article on the 6 passes outside Glacier National Park, try these search words. Belair's paper on Glacier National Park was posted in December 2015. These search words should find the journal article, but it may also take you to an earlier unrefereed paper from the 2013 ISSW. Alternatively, to find Belair's journal article, try ASARC Node 353. Thanks for your interest in these studies of trends in snow and avalanche climate.